All right, well, the other day we looked at vectors in both two space, which is two-dimensional, and in three space. And so what we're going to do is today is look at operations of those vectors in both two space and three space. And so example 1 here says, draw the position vectors A, 5, 3, and B, negative 4, 2, on the xy plane below. All right, so the number 5, or the vector defined by A, 5, 3, would mean from the origin to the tip, which is at 5, 3. So let's see here, move right 5, up 3. And so from the start to the finish, that's supposed to be a straight line, by the way. All right, and that would be our vector A, or OA, with vector symbol on it. Let's put that in there, and we got a little 5, 3, comma. And then we also had, let's see here, vector B, which is negative 4, 2. So again, starting at the origin, left 4, up 2. So we can draw a nice straight line. There we go. All right, so that would again be vector OB. Now, we have these two little vectors that I've drawn out there, which are I and J, which are our standard basic unit vectors. Again, unit vector means you have a magnitude of 1. And I is what we call the horizontal component of our vector, or a unit horizontal component. And J is the unit vertical component. And so we get to the next part here where it says write position vectors A and B using the standard basic unit vectors. And so if I had vector OA and it's at 0.53, well, writing it in terms of our unit vectors, well, it would be 5 i's plus 3 j's. Would be it broken up into its standard unit vectors. Just like B, which is the point defined by negative 4, 2, well, we went 4 to the left, so negative 4 j's plus 2, negative 4 i's plus 2 j's, 2 up. So again, I and j are our standard unit vectors. I is your horizontal vector, and j is your vertical vector. Now, looking at finding the magnitude, we have the magnitude of OA. All right, now if I'm going to find the magnitude of OA, well, I'm just going to use the fact that I could create a Pythagorean or a right-angled triangle and use the Pythagorean theorem. And so that the magnitude of that vector OA is I'm going to take the square root of one of the legs of the sides. Let's see here, we got 5, so I'd have 5 squared, plus the length of the other side, which is 3, and 3 squared. All right, and so in that square root, I got 5 squared, which is 25, 3 squared, which is 9, and let's see, if I add those two together, I get the square root of 34, and I pump that into my calculator, and I get 5.83. All right, now I could do the same thing with the magnitude of OB, but I'm going to skip a couple here and there. All right, now we get to find A plus B, so we're adding vectors. All right, and so what I'm going to do, because the only time we've added vectors is that we've drawn diagrams to add vectors. Well, I'm going to use my vectors drawn or represented as unit vectors, broken up into unit vectors, and I'm going to add them. And so that if I have A, which was, let's see here, 5j plus 3i, all right, so I'm going to put that in there. I have a 5i plus a 3j. All right, now I'm going to add b to it, and the b vector was negative 4i's plus what was it, 2j's. All right, now what I can do when I'm adding these two vectors together is that I can add the like terms together, or the like vectors, I should say, together. So I'm going to put 5i, well, minus 4i together. And in a similar way, I'm going to put the 3i, or 3j, plus the 2j. So in terms of components, a plus b, well, I'd have 1i plus 5j's would be the vector a plus b. And again, I can find the magnitude of that vector because I have the triangle. If I was to add those two vectors, essentially I'd be 1 to the right, 5 up. And so I'm looking for the resultant here. And again, it is a right-angled triangle. And so again, I'm going to use the Pythagorean theorem, where I take the square root of, well, on this side, one of the sides is 1, so we got 1 squared plus 5 squared. And so let's see, 1 squared is 1, 5 squared is 25. Add them together, that's going to be a 26. And if I take the square root of 26, I end up with 5.1 would be the size of that vector, a plus b. Now we can also look at a minus b. And again, it's just like using polynomials, where, let's see if I can steal this. There we go. Oops. So if I want a minus b, this time I'm just going to do the same thing, write my vectors out in terms of their components, and then when I'm going to subtract these two vectors, I would have 5i. Now I have two minus signs there, minus 4i, which means the opposite of negative 4i, which would be actually positive 4i. So again, just like math, positive 3j, and then I have a minus 2j. All right, and so if I find a minus b, well, it ends up being 9i plus 1j. And again, I can find the magnitude of that vector. But again, using the Pythagorean theorem, in this case, I'd have a 9 squared plus a 1 squared again. 9 squared is 81. 1 squared is 1, so I'm just going to take the square root of 82 this time out. And I end up with, let me see here, I get 9.06. Again, would be the size of a minus b. Now, here's one that's a little bit different, is that if you're trying to find the vector AB, which really means you take OB minus OA, which really means you're taking B minus A. So in this case, so that's something to watch out for, is that if you're finding AB, it's really B minus A. And so in this case, that would be, B was again minus 4i plus 2j. All right, and again, we're subtracting, and our A vector was, I'm going to have to look at my sheet again, I forgot. Oh, 5i plus 3j. Again, written out as components. And so what we'd end up if we expanded that negative sign through the second bracket is I'm going to have a negative 4i minus a 5i minus, let's see here, oh, not minus, so plus 2j minus 3j. And so we end up with, let's see here, minus 9i minus 1j. All right. And whoops. Oh, what did I do there? Oh, there we go. All right. Sorry about that. All right, now I want to find the magnitude of AB. Well, again, I'm going to use the Pythagorean theorem. And we have one side here which is a minus 9, so I have a minus 9 squared. Plus, the other side is a minus 1, so I'd have a minus 1 squared. And again, minus 9 squared is 81. Positive 81, negative times a negative, and then negative 1 squared is 1. So again, I'd have the square root of 82, which lo and behold, guess what, is equal to 9.06. And so if I go up here a bit and I look at the fact that I have a minus b and I have b minus a, and look at the vectors, they are the opposite of each other. That's all. They're in the same, they're parallel but in the opposite direction, but have the same magnitude. All right. Now, the other thing is, what we got here? When we're looking at what's called scalar multiples of vectors. And so in this case, I have two vectors. And the first one is 3i plus 2j. And I have another vector, which is negative 4i plus 5j. And what I want to find is, actually I'm going to change this up here. I've got, I want to find out what 2x's plus 4y's are. So again, this is scalar multiple of two different vectors, but yet we're adding them. All right, and I'm going to find the magnitude of that vector, 2x plus 4y. But just like using polynomials in math, we can do the same thing with vectors. And that when I have two x's, well, that means I'm going to have 2 times, and x is 3i plus 2j's. And then I've got to add it to 4y's, and y's are negative 4i's plus 5j's. All right, so then I just expand where 2 times 3i is 6i. Then we have a positive 4j. And then over here in the second bracket, 4 times negative 4i's, well, that's a negative 16i's. And then 20j's. Oops, 20j's. I should put positive 20j's. There we go. And then again, just like polynomials, I can put my j's together. So my i's and my j's together, like vectors, just like terms. And so 6i minus 16i is negative 10i's. Negative 10i's. And put the j's together, I would have 24j's. Positive 24j's. All right, and so then again, when I'm finding the magnitude of this vector, again, there's some vector symbols over these i's and j's because there are standard unit vectors. Well, I'm going to use the Pythagorean theorem again, where I'm going to have negative 10 squared, even though I don't really have to put negative 10 because the length is still 10. It's just in the left direction, plus 24 squared. And, well, I don't know these numbers off heart, but except for negative 10 squared is 100. 24 squared. Let's see here. We end up with 576. And it looks like I'm going to take the square root of 676. So let me see here. Square root of 676. And I get, whoa, 26 right on. And there we go. So even though we're using vectors, we're using a lot of the same skills you would use in math. They're basically, you can almost treat them as polynomials. Now, where things get a little bit